Welcome to Ideas in Action, the official University of Southern California podcast. This show was recorded live on USC's campus.
Okay, I think we are live now. Good morning, everyone. And I want to welcome you to the USC Facebook Live broadcasting. We're broadcasting live today, virtually, of course, from Southern California, USC, and the California Science Center. Today, we're going to spend the next hour talking about Mars. It's a great place. We're going to learn something about it, how we get there, and how we study it. My name is Ken Phillips. I'm the curator for aerospace sciences here at the California Science Center. I'm also a professor of physics and astronomy at USC, the Dornsife College. It is my pleasure here to welcome a very distinguished panel and to thank you for joining us. Please do send your questions to us via the comment box, and we'll address as many of those as we can throughout the course of our discussion and, of course, at the end. And by the way, please like and share this video with others. We want to help build interest in this effort. This is a collaboration between the California Science Center and the University of Southern California. We've done many collaborations as an institution, but this is a first in terms of our public outreach and media. So we're very excited about this. And we're going to be talking about what is going to happen next week. NASA is going to launch a rover to the planet Mars. They've done that before, but this one is of particular interest. And it is scheduled for liftoff on July 30th. That's coming right up. And it's a very important mission. The goal is to search for life and test the ways that Mars might support humans. So we'll know what to expect when we get there. And to set the stage for a manned mission to the red planet. It's going to be a very exciting thing. Now, joining me today that you'll see on screen are three very distinguished experts and colleagues. I'll begin by introducing Dr. Kenneth Nielsen. Ken Nielsen is Professor Emeritus in the Earth Sciences at USC Dornsife College. He is an expert in the search for life in extreme environments. What does life look like? Where do you find it? How do you know it when you see it? He's the founder of the Geobiology program at USC, and he's also a founder of the Astrobiology program at NASA's Jet Propulsion Laboratory here in Pasadena. He's also a member of NASA's Mars Science Team. Very distinguished professor. Thank you for joining us, Professor Nielsen. Dr. Anita Sengupta. Professor Sengupta is a professor of astronautics at the USC Viterbi School of Engineering and a former engineer at JPL. Anita is an expert on spacecraft design and interplanetary exploration. She was responsible for the supersonic parachute system that landed the Curiosity rover on Mars. And if you've ever seen the animations to that, it is just unbelievable what they accomplished. Thank you very much, Anita, for joining us. And I'm looking forward to your comments today.
Thank you.
And then finally, certainly not last, certainly not least, last but certainly not least, is Dr. Garrett Reisman. Professor Reisman is also a professor of astronautical engineering at the Viterbi School. But he was a NASA astronaut for many years, flying on 3 separate space shuttles and spending months aboard the International Space Station. He was also the former director for space ops at SpaceX and still consults with that company. So Garrett, thank you so much for taking time from your vacation to join us today.
No, it's my pleasure. Good to be with you.
So we're going to talk about Mars in a minute, I promise you. But right now, I'd like you to meet the panel a little bit, get to know who these people are. Very special group. And I want to begin with a general question that I'm going to call the cool factor. Okay, we'll talk about the specifics later. But right now, I'd like to ask each of the panelists to reflect a little bit about why space exploration, the exploration of our universe, and the exploration of our solar system in particular is just so cool. Independent of any particular mission, it's a cool thing. And Professor Nielsen, why don't you start off with a response to that and everybody just sort of chime in.
Sure, I'm happy to do that. I can't imagine anything more human than wanting to know about the environment, the universe. We know a lot about our own planet. But you imagine that the ancients, the Greeks, were asking the same questions that we're asking now. You know, are we alone in the universe? Is there life elsewhere? All they had were their eyes. And by golly, they came pretty close to getting it right. Okay, they had the Earth in the center of the universe, but that was a small thing. But the amazing thing to me, the really cool thing as a biologist, is the way technology has driven us. For invent geometry and mathematics, then they invent the telescope, then they start flying around the planet, and the stuff you're going to see today is mind-boggling to a laboratory freak like myself. I'll pass it on to Anita here.
Yeah, and I definitely reiterate that understanding your place in the universe, are we the only life out there, is just probably the ultimate question for every sentient being. And also the tremendous engineering challenge to be able to cross the vastness of space really does drive our abilities as a species, and challenging our minds, our bodies, and our perceptions of what's really out there. I'd like to pass it over to Garrett.
Yeah, I just echo what everybody else has already said, which is that the desire to explore and to learn is a very human thing. Like Kenneth said, it's something that we're all born with. I remember as a little kid growing up in New Jersey, I would go out and into the woods behind my house, and I was very curious to see what's on the other side. It was something that drove me. And all the exploration we do in space, whether it be human or robotic, is just an expression of that human need to see what's around the corner.
Great answers. One of the things that's occurred to me is, and each of you sort of are representative of this, the exploration of space is a very interesting thing. In theory, given that we are on a planet that's orbiting a relatively odd red star, in the outer arm of the galaxy, of which there are billions in the universe, you would think we shouldn't know anything about the universe that we know. We're arguably in the worst possible perspective to figure out this thing, and yet we have. And the way we've done it, which is amazing to me, is the Earth has somehow supplied us all the materials that we need to do it. We didn't have to go anywhere to do it. I mean, all of the things that we're doing, the telescopes we build, the spaceships we climb in and fly, the robotic probes that we send from place to place, those are things that the Earth has provided. If you understand how to take the raw materials that are under your feet and transform them into things that extend your own human senses, that to me is an amazing thing. And I think each of you represent a little bit of how we do that. Professor Nielsen, from the perspective of the scientist who's asking the questions, and of course, Professor Sengupta, from the perspective of an engineer who builds these things, and of course, Dr. Reisman, from the perspective of somebody who actually climbs into the spaceships. He actually doesn't look crazy, but he climbs into the spaceships and then flies to places that hopefully more of us will get to visit in the future. So before jumping into the Mars specifics, I want to ask you each a specific question just to help the panel get to know a little bit more about you. There are many things you could have done in life, and yet you've chosen the path that you've chosen. What made you do that? Was it like an epiphany experience? Was it somewhat of a milestone event? Or was it a gradual awakening to how exciting all this was? How did that happen for you? And Professor Sengupta, why don't you start off with that?
So I have a very clear story, and that is my love of science fiction. My father was a mechanical engineer, and we would watch Star Trek, reruns of the original series and then Next Generation when I was a little kid. And I just knew I wanted to facilitate the exploration of space and hopefully meet alien species. So that was absolutely my motivation. And I was pretty much laser focused from the age of 6 on.
Okay. How about you, Professor Nielsen?
Well, I'm the old man of this group, I guess. And I was profoundly impacted by my high school science teacher, who dragged us out of class in the evenings and made us watch the Sputnik passing over our planet. It really transformed me. I started building rockets. I started wanting to do this. And then in the university, I discovered just how tough life could be, and the thought that it might exist elsewhere in places that people were disregarding the possibility, again transformed me. This complex toughness of life changed my view of where one might think there could be life. I wouldn't say I was laser focused, but between these two kinds of events, it really made me want to spend my life doing this.
Yeah, nice. Garrett, how about you? What's your story?
Yeah, Ken, me too. Star Trek, my high school physics teacher, Mr. Vandervoort, but also a science museum. So when I was about 13, my family took a trip down to Washington, D.C., and we visited the Smithsonian's National Air and Space Museum.
Yes.
And the plan was to spend like a couple hours there, and then I think we're going to the Lincoln Memorial. And they said, okay, we'll split up, see what you want to see. We'll meet back here in about 2 hours, and we're going to leave. And then after 2 hours, I came back and I told my parents, I only covered one room in this massive facility. I need 2 more days here. And so I still haven't been to the Lincoln Memorial, actually. They went on, they saw everything else. But I spent 2 days, and they kept coming back to check on me. But I spent 2 days in that building, and I was just fascinated by everything that it contained, and wanted from a very young age to be part of human exploration of space. I thought it was just the coolest thing ever.
Fantastic. So you all got bitten by this thing when you were very young. That's amazing. That's sort of consistency in your story. And we'll have a lot to say to motivate young people who hopefully are joining in on this this broadcast today, because we want to make sure that they know they are very much needed to, we're going to pass the baton to them, you know, and when we do that, when we reach back and say, hey guys, come up to the plate, you know, it's your turn. We want to make sure we have an excited and motivated group of young people to kind of take over and move all this exploration forward. So now, without any further ado, let me get to the actual, and here we're going to do a little technology. We're going to test our ability at mission control here. I'm going to see if I can play video. We're going to get right into this Mars mission. I'm going to play a 3-minute video. It's going to be an overview of the Perseverance or Mars 2020 mission, which again will launch in just a few days. And it'll give you at least a cursory view of what the cool technology is and where the specific research questions are on this. So if I can do that here. Here we go. And I've got to share my screen. Remember to do that. Now give me a confirmation, guys. Can you see that? Fantastic. Here we go.
NASA's next Mars rover is in development and has an ambitious mission. Decades of Mars research from previous spacecraft have shown the planet not only had water in the ancient past, but had environments that could have supported life.
Mars is our neighboring planet, and in many ways the most similar to us, and certainly in its history. And the question whether ancient life was there is still the question that keeps us up at night.
Mars 2020 has 2 new objectives: to specifically seek the signs of life, and then sample materials and prepare a cache that could be returned to Earth by a future mission.
Mars 2020 is really the essential first part of a sample return mission. So it actually looks at the environment of these samples and then collects them and stores them. Afterwards, we will, of course, go and bring these samples back. So Mars 2020 is the first act of a return trip.
The Mars 2020 mission, to the maximum extent possible, follows the Mars Science Laboratory Curiosity mission. We're going to use very similar rocket, very similar cruise stage, very similar entry, descent, and landing. And the rover, when you step back, will look almost identical.
Not only were a lot of designs already developed for the most part, but we're also using a lot of spare hardware that we had from MSL or Curiosity for Mars 2020. If you know where to look on Lab, you can walk around and see a lot of the EDL hardware and the cruise stage hardware that's already been built.
And this is really important for understanding why this mission makes sense. We have to do relatively little in the way of new development. And this saves money, it saves risk, it saves time. It's the right way to pursue this kind of mission.
Mars 2020 also features new technologies for entry, descent, and landing, allowing it to target a smaller landing zone and even divert from known risks in the area.
It means that we can both go to places that are maybe more interesting to the scientists because we're able to handle places with more hazards, as well as land closer to the things that they're interested in off the bat. So we get to the science that they care about and more quickly.
The 3 key sites that we are considering right now share one thing in common. They are all environments that might have been habitable in the very distant past. One of them is the floor of an ancient lake. Another is a hot spring. And the third one is a site where hot water interacted with rocks in the shallow subsurface. We have instruments on board which are expressly designed to seek evidence of ancient life, what we call biosignatures. And we have the capability to prepare samples, drill them out of a rock, seal them in a tube so that a future mission could go and bring them up. We call that caching.
So it is a first of a new type of mission, which is to bring samples back to the best labs we have, which are here on Earth. Mars 2020 is a pivotal mission in our search for life that could finally answer the age-old question, are we alone?
Okay, that was pretty exciting. I think we'll have to agree. This is an aggressive mission, and obviously it is something that is coming on the heels of a lot of prior exploration that's taken place at Mars and other places in our solar system as well. I've got two questions for you, having looked at this video. The first is a technical question and involves the importance regarding science, and the other is an impact question. I'll ask the first question. And it's basically, we've just seen this really cool video. It's an overview of an exciting project, and from a scientific perspective and an engineering perspective, what does it mean to the human ability to explore? What does this mission do for us that we hadn't had at our disposal before? Garrett, why don't you begin?
Well, I think, part of the mission objective is to pave the way for future human exploration. So obviously, this is going to answer a lot of fundamental science questions, we hope, and get a lot, and probably raise a lot more questions. Usually, the more we learn, the more we have to ask. So I think that's going to be fascinating. But also, from a human exploration standpoint, there's going to be elements of this mission that will really help us in the future when we talk about sending humans to Mars. And part of that is, understanding the atmosphere better. There's going to be a demonstration of getting oxygen out of the atmosphere, which is something we can really use for human missions. And really, the other thing is finding out more about the signs of life and the presence of potential Martian life, and how we can protect those discoveries, make sure we don't contaminate it when we do go there with humans.
That's a good point. Yeah, Professor Nilsson, why don't you respond to that question again from your perspective as an astrobiologist? What will this mission do?
Well, I think Garrett really hit the nail on the head here. If we're looking for human habitation of Mars and human exploration, we need to know more than we know now. This mission is going to have a lot of instrumentation searching for water and learning about where the water is on Mars. And we're creatures of the water. We need to know where the water is and how to access it. That's number one. I think number two, we'll never know unless some green man jumps out from behind a rock. We'll never know about finding life on Mars until we bring some samples back and really have the technology we have on Earth to prove that there is or was not life in those samples. This is another biggie because the whole issue of planetary protection and protecting the planet from us and vice versa lies in that knowledge. So I think this is a very important mission, as Garrett said, to plan the next missions.
Fantastic. And Professor Sengupta, what do you think from an engineer's perspective? I mean, you design these spacecraft that go to these places, and your specialty is entry, descent, and landing. How do you get them onto the surface in one piece? So share your thoughts on that question. What does this mean to the next robotic probes that you'll be designing? How does it help?
Sure. So one of the most difficult things to do from a spacecraft design perspective is to land something on the surface of another planet because of the precision which is needed, because of the challenging requirements that you face from a heating perspective, from a loads perspective, and from a precision perspective. And one of the things that this mission does, which is brand new and is key to landing people on the surface of Mars, is develops two new technologies, which we just heard from Marissa, my former colleague from JPL. One, which is a range trigger, which actually tells you when to deploy the supersonic parachute, and that will allow you to reduce basically your error of where you are relative to the surface target, so you can get even closer to the surface target, enabling a more precise landing. And the other one is terrain relative navigation, which allows the rover itself to detect hazards on the ground and avoid them and execute a divert maneuver. So when we eventually send people to the surface of Mars, we'll have to have sort of a pinpoint landing capability. And these two new technologies, which are being demonstrated by Perseverance, are key to that landing system for humans on Mars.
Fantastic. Now, I've heard it said, tell me if I'm wrong about this, that here's the thing about Mars' atmosphere. It's about 1% of Earth's in terms of its density, right?
Yes.
The problem is it'll burn you up if you don't protect yourself against it, but it doesn't do you any good. It doesn't slow you down because it's not thick enough to do that. So it's just a nuisance. Is that right?
It is. The good news, however, though, is that it does provide you with aerodynamic drag, and you're able to dissipate a lot of the energy, even though the atmosphere is so thin, but you don't get the traditional lift forces that you would here on Earth. So you can't use it as much for control purpose, but you still can. But certainly it's the biggest challenge from a G-loading perspective, from an thermodynamic perspective, to be able to land precisely on the surface. And of course, the rover has to do it itself autonomously because it can't communicate back to Earth during that short time interval.
Yeah. So here's the second question. We're going to get to Mars's atmosphere in a minute because it's going to play a crucial role in the Ingenuity project, which I'm going to have you reflect on in just a second. I'll show you another video. But before we do that, my second question involves impact. It's more a philosophical question. It's this. This is an amazing undertaking that we've taken as humans. Professor Nielsen, I'd like you to respond to this question first and then others chime in. Suppose we actually do find life. What will that do to us as human beings? What will it do to us? What will it do for us? How will it change us?
Yeah, that's a wonderful, those are our wonderful questions. What will it do to us? It'll provide one of the answers that we've been searching for as a species for our entire existence, in a sense. So it would be monumental discovery. I think what it does to a given human is a very personal thing. It has overtones of religion. It has overtones of belief. It has, for me as a scientist, overtones of what are the next questions we can ask. If we don't know there's other life, we're really constrained by the types of questions we can ask. If we do know there's other life, it opens up for the next generations a million questions. And this is so fantastic. So I think it would do for us much more than it would do to us. I see that at the individual level, we would all have a response, but as a species, it would really do fantastic things. I think the next generation of scientists would be served a wonderful meal on the platter by that discovery.
Yeah, interesting, yes. Professor Sengupta, what do you think?
So I think it would help us to understand our humanity better. So I think lots of times we see challenges here on Earth, and that's because people are focused on the differences between us and our neighbors. We're us in a different country, where in reality, we're all human beings, and so we're all Earthlings. So I think it will help us appreciate our place in the universe. I think it will probably give us a better focus on how to protect Earth from a climate perspective, and hopefully it would actually just make us better people and be kinder to each other.
Interesting. Eric?
Yeah, all that's true, absolutely. And I'm struck by a comment that Professor Nielsen made actually earlier in this broadcast, which was talking about the ancient Greeks figuring out that, or having something wrong, which is they thought that the sun went around the earth, right, with Apollo driving his chariot and whatnot. So I think that the discovery of life on Mars, the best analogy I could think of would be perhaps the discovery that, the Earth is not the center of the solar system, but the Earth goes around the sun. And at the time that discovery was made, it was very profound. I mean, it had massive theological connotations. It had massive scientific impact. Today, I think we all understand that the Earth goes around the sun, or at least most of us.
Yeah.
And so on a day-to-day level, it's no big deal. But the thing is, it profoundly changed the direction of our investigations, the direction of our philosophy, the fact that the Earth is not the center of the solar system. And it paved the way for all the science and exploration, and it really served as the foundation for our future direction. I think finding life on Mars was similar. And there'll be an initial massive impact theologically, philosophically, scientifically. But the real impact will be its lasting legacy, which is that if we know that life is really as tough as Professor Nielsen has mentioned it is, that maybe we'll find it everywhere. And that changes where we look and what we do go forward in ways that we can't even predict.
You see, that brings to mind, when I was a kid, I used to love monsters. I still love monster movies. In fact, I raised my children on pizza, Pepsi, and monsters. So anyway, but that's another story. So what I jump to is this thing of like, given the probability that life is elsewhere in the universe. It may take some incredible forms. There must be some scary stuff out there, but there'll be some cool stuff out there too, you know? And maybe it looks like aliens, and maybe it's like the day the earth stood still. I mean, it could be anything. And so, you know, my mind from a popular perspective goes to this genre of film and literature that has to do with the various forms that life could take. You know, what will E.T. look like? And Garrett, you might be the first person to shake hands with one, given what you do.
Well, I'm not shaking hands with anybody these days, Ken.
That's very good.
Who knows what virus ET has, for crying out loud? There's no way I'm shaking his hand.
Yeah, the planetary protection thing that we mentioned before. So this is great. I wish we had time for this conversation to go deeper into this. Maybe that'll be a future show. But indeed, this is an amazing set of questions, many of them philosophical and theological, that the discovery of life could imply for us. And the interesting thing is that we are on the verge. I mean, this isn't the theoretical conversation we're having. I mean, we're spending $2 billion plus to get a spacecraft on the surface of a planet that could actually answer that question. I mean, it's not a joke. That's the amazing thing about this whole thing to me. So now I want to come back to the mission specifically. And I mentioned the atmosphere earlier. I'm going to show a video, it's enormously exciting. It's part of this mission, something we've never done before. And at the end of the video, Professor Sengupta, I'd like you to lead off with a series of comments about what it means to us. Okay, so I'll see if I can bear with me here for the technology. I'll close the other video so I don't show it again. And then I'll open up the new one. And the new one is about a project called Ingenuity. And I hope everyone can see. I do my screen share. Let me share the screen. Okay, first of all, give me a confirmation. Can everybody see this? Okay, fantastic. Okay, now I wanted to share that video because it raises the question of risk and challenges associated with all of these things that we're doing. Whether one is a scientist and creating an instrument that one hopes works, whether one is an engineer and creating a spacecraft that's got to land safely and perform, or an astronaut who obviously is depending on the excellence and the due diligence of their crew and the people who created their spacecraft to get them safely to and from where they've got to go. So, Professor Sengupta, please talk. What did we just see in that video? That looked amazingly complicated to me. A lot of things have got to go right the first time. So just share what it means to deal with the risk and the challenges associated with making all of this exploration possible.
So if I focus in on Ingenuity itself, which is a rotorcraft, a Mars helicopter, a fully electric vehicle, it is a technology demonstrator. So what NASA does really well is at each mission, they try and feed forward new technologies for initial demonstration, which aren't key to the primary mission success floor, but will enable far more scientific return during the current mission as well as on future missions. And so what Ingenuity is a counter-rotating platform. It has to operate purely off of electrical energy, which means it has a solar panel and a battery. Because the Martian atmosphere is only 1% of Earth's, it does have lower gravity, less than 1/3. It has to be able to generate enough lift with that tiny thin atmosphere. And so it does that by being very lightweight and having big rotor blade. So basically that platform that you see weighs about 5.5 pounds. It's got a rotor diameter of less than 4 feet, and it has a sort of a cubical body of about 5.5 inches. So the engineers had to make a platform which was incredibly lightweight, incredibly mass efficient to facilitate a 22-mile-an-hour cruise speed, and it goes for about a 90-second flight per day to collect reconnaissance images of the surface. And when you have an aerial platform like that, being able to do close to the ground aerial surveys is a brand new capability which will really facilitate scientific exploration.
That's really exciting. That's really, really cool stuff. Professor Nielsen, talk about risk from the perspective of someone who is trying to determine where life might be hiding, and you want to be highly confident if you say, yes, we found it. How do you know life when you see it? What are the risky parts of what you do as a scientist, specifically searching for life in our universe?
Well, we're stuck here, aren't we? We know about only one kind of life, and one of the classic mistakes we make is to assume it's going to be like our life, and that we use the techniques that focus on the molecules of our life. Sure, it could be that way, but it doesn't have to be that way. One can dream up all kinds of variations on the theme. I've always wanted to put a project together to look for different life on our own planet. We would never recognize it if we ran into it because we're measuring the wrong things. So I think that there are fundamental, simple questions that you can ask about what life has to be like, not about what it's made of, and focus on those kinds of questions. We haven't gotten to that point yet. It's the only thing I can find bad about getting old, is that we probably won't get to that point before I'm out of the fun. Life probably has to be cellular. It probably has to separate the inside from the outside. It has to take up energy. It has to give off waste. Those are all things that if we sit down and do the basics, we would say this is what you look for. And I think we have the technology to do it. And if not, certainly the next generation will.
Right. And would all life, would you say, have to reproduce itself? Or is there a life form that could come into existence in some way or from some origin and then never have to reproduce itself, live forever? Is that a thing? Or is that by definition not a thing when it comes to life?
Probably it isn't a thing. I think if you have life that's going to really change a planet, really dominate a planet, really succeed, probably replication is a really important thing. It has to make copies, and making the copies allows you then to evolve because every copy won't be exactly like the other ones. So if you're going to be able to adapt to a changing environment, you need probably this replication. The problem, of course, is that we now have bacteria deep in the earth that only double every 100 or to 1,000 years.
Yeah.
So this is going to be very difficult to use replication as a thing to hunt for.
Absolutely, absolutely. Garrett, what about your perspective on this whole thing? The risky aspects of technology, of taking major leaps. These are not really incremental steps that we're taking, at least as I see them. These are big deal increments that we're jumping in here. What do you think?
Oh yeah, and so we just heard a great description of kind of the risk or the potential or the difficulty in the scientific discovery about life form. But I'm an engineer, so from an engineering perspective, I'm fascinated by this mission because there's so much complexity in this vehicle. I was fortunate enough to be up at JPL when Curiosity landed, and during what they call it, the 7 minutes of terror, I think, which is all the sequence of events that had to go correctly, and any one of them, if it failed, could lead to catastrophe. And I'm just really amazed by the coolness factor of this whole mission, especially that helicopter. I can tell you that my son and I, we've been flying this RC controlled airplane, and as you can see, we had I'll try to make sure, I don't know if you can see that there, but we had quite a mishap the other day. It's not easy to get these things right? So I would like to actually turn around and ask the question of Anita and ask, having gone through the whole 7 minutes of terror with Curiosity, are you feeling less terrorized when we approach this Perseverance landing?
So
You've done it once, and then of all the other things, let me leave it at that. I'd like to hear your perspective on that.
So the good news is that each prior mission builds on the prior mission for that. So in terms of building up models of the atmosphere, in terms of building up aerodynamic models of the vehicle, even the parachute, for example. So the parachute, where I did a lot of the supersonic quantification from Curiosity, was very similar to the parachute before, a bit bigger. And this particular parachute is very, very similar to the one that we did from Curiosity. So when you have that heritage, you do reduce the risk associated with it from an engineering perspective, from a cost perspective. But ultimately, each time one of these missions goes off, it is so challenging because every single element is essentially a single string and it has to work the first time. And from a probabilistic assessment, just doing one mission every decade obviously doesn't reduce most of the risk associated with each event. But there's so much engineering that goes into it. There's so many brilliant people working together, and they live, they eat, and they sleep this for their lives for 5 to 7 years, that it is going to go as well as it possibly can, as long as they don't have a really, really bizarre day on Mars. And even that, you build into the design a lot of margin, both in terms of aerodynamic performance of the vehicle, in terms of understanding how the atmosphere might vary on a given day. So they're doing everything they can from an engineering perspective to get it to work this one time.
So you say that from an entry, descent, and landing perspective, we're still going to have at least 7 minutes of trepidation.
I think so. Yes, definitely.
Trepidation. Yeah, I like that. Yeah, that's improvement. That's progress. That's progress. That's great. So let me ask you now, from your own individual perspectives, each of you must have had a nail biter moment of some sort in your own career. Okay. Garrett, I'd like to lead, if you would be so kind, I'd like you to lead the initial response to this. You shared a story with me some months ago about something that happened in one of your spacewalks. Now, there could be other things that would be nail biters that come to your mind, but if you think that one's appropriate, share that, because it was an amazing story about how one has to be fast on one's feet. In other words, it's the advantage of confronting something that you don't expect. You've done your homework. You've done everything you can do to make sure things go, but then there's a snafu. Something goes wrong in the operation, and you've got to make a split-second decision, and you've got to stay calm, and you've got to make the problem go away. So share that.
Yeah, I don't want to dive too deep into the whole humans versus robots age-old thing here, because when artificial intelligence takes over and we have our robotic overlords, if I say something bad right now, they're going to come and send killer finder robots to get me. So I don't want to go there. But I could tell you one of the advantages that we have on human missions that you don't have, which is why you do have 7 minutes of real terror or trepidation, is you have the ability to adapt and be flexible. And the difficulty in accomplishing what this mission, what Perseverance is trying to do, Mars 2020, is the fact that everything has to be perfect and foreseen and planned in advance. And you have to have no failures of imagination. You have to be able to program it and design it perfectly so it all works without changing the plan in midstream. Now, when you're doing a human mission, you have more ability to adapt and be flexible. So one of the story you're talking about, Ken, I think, is when I was doing one of my spacewalks, we had a connector that we were plugging in this big antenna on the top of the space station, and we had an electrical connector. And then we had a certain amount of time that we had to make sure that plugged in successfully, or we couldn't get power to the heaters and the thing was going to get too cold and die. So we were on the clock to get this done. And when we went up there and went to plug it in, the connector didn't fit. The male side was just too big, and we were pushing and trying really hard to make it connect. And no matter what we did, we couldn't get it to work. And we realized that we had, about another 30 minutes or so to figure this out, or we were going to lose tens of millions of dollars of equipment and a major mission objective. And so as we sat there trying to think about what to do, I asked the pilot of the shuttle. I said, "Hey, we're in eclipse right now. We're at night because the Earth is between us and the sun. When does the sun come up? How long until daytime?" And he said, "About 10 minutes." And I said, "Okay, great." So what I did was I took the male end and I covered it up with my glove and I put it behind the pedestal that the antenna sits on, so it would be shielded from the sun. And when the sun came up, it's shown on the female end, and the temperature difference in space could be hundreds of degrees, depending on if you're in the sun or in the shade. And so we let the sun hit the part that needed to expand, and that temperature made it expand a little bit. And then I quickly took the other end of the connector and plugged it in, and it fit perfectly, and we saved it. Now, that was not the plan. We did not, have that in the procedure, but it was something we came up with on the spot that saved the mission.
Fantastic, fantastic. Professor Nilsson, can you think of a similar instance in what you do that caused you maybe to think faster on your feet? Maybe something you were designing and it wasn't going the way you thought it would, and suddenly you had to switch gears and almost at the last minute to make sure you got the a credible analysis that you were going for.
Oh goodness, I wish that were true. I think, but one of my messages to the students here is that we need all kinds of people doing different things to be successful. And I would say the biggest trepidation that I've had over the years in science is trying to do something that everybody thought wouldn't work. The example I'll give you is that we discovered 25 years ago bacteria that didn't breathe oxygen, but they breathed metal oxides instead. And breathing is just moving electrons around. And these bacteria, no one believed them at the time. But in fact, they take organic matter, sugar, whatever, and they can convert it into electricity via this breathing. So we can build fuel cells using bacteria that eat things. It took a number of years to get anyone to believe this. And now the aftermath of this is that we have bacteria that will grow using electricity for their energy source. These are things, in fact, when it was published in Popular Science, they called them aliens because they didn't believe it. That's a different kind of a gee whiz moment, and it's much more attuned to the kind of work that I do. Darn, I'd like to be on one of those spacecraft. So,
yeah, wow, great. And Anita.
So I have an example from my Mars Science Laboratory Curiosity days. We were doing our very first parachute test of the Canopy, which obviously landed the rover and is going to land this next rover, and it failed catastrophically. Basically, it just shredded into pieces in the sky. And so we didn't want to cancel the whole test program. So we had to come up with a way to figure out, number one, what went wrong by looking at the video data that we collected, and then what could we do to perhaps expose the Canopy to a slightly lower load so that we could still learn things about how it inflates and how it performed. And so we dumped our mortar deployed Canopy test apparatus, and we came up with basically a pull Canopy apparatus, so it comes out of a bag. And that way we were able to continue the test program and still generate a lot of interesting engineering information. And we learned from that failure on where the Canopy failed, where to reinforce it. And that's basically the design that you'll see going forward with today. So when you do stuff out in the field, oftentimes you're forced to jerry-rig solutions and come up with really fast ways that you continue to make progress. And all engineering is about is actually learning from your mistakes and improving upon them in many instances.
Fantastic. Wonderful responses. We're going to talk about the future in a minute, and I want to make sure there's time for questions. Before I do that, I'd like to ask you, we've talked about challenges, we've talked about solutions, but there must come to mind for each of you the most satisfying, if such a word can be used or such a phrase is appropriate, thing that you've ever discovered or done in your work. What comes to mind is the most satisfying and rewarding experience that you've had? And I know that's a tough one because they're probably, given as distinguished as you guys are, there are probably many such times that you've had epiphany moments or things that are really, really important and memorable. But if you can think of one, share it.
I can think of one. Excuse me, when I was at JPL, we set up the astrobiology group, and one of our goals was to invent a microscope that would work without having to stain the living organisms. And the idea was to use a different wavelength of light, what we call deep UV light. And it turns out that we worked on it for several years at JPL. I moved to the University of Southern California, and my #1 student who worked on this at JPL ended up getting his PhD perfecting that microscope, and it will be on the 2020 rover when it lands on Mars. This was absolutely stunning for a microbiologist to be involved with these brilliant engineers who could take this microscope, which was 3 feet across, and it now sits on the end of the rover arm. Wouldn't be better.
That's really sweet. I like that. Anita, how about you? Got anything you want to share on that?
Yeah, and this I'll plug it back to USC. So I did my doctoral research at USC in the Aerospace Engineering Department many years ago, and I was able to conduct all of my research whilst I was also working full-time at JPL, and I was running a test bed of the Ion engine for the Deep Space One mission on the ground at the same time as the engine was running in space on the Deep Space One spacecraft, and the spacecraft was having this on-orbit problem where it was seeing these high-energy particles coming out of something called a neutralizer, which is the way you neutralize the beam coming from one of these engines. And so I was able to wire up an instrument on the ground in our test bed to simulate what was happening on orbit, and then propose a change, demonstrated the change on the ground to basically clear out this this device called a neutralizer. And then we were able to implement that on the spacecraft and then solve the spacecraft's problem. And of course, that went straight into my PhD thesis work. So it was really satisfying because I could do it, see it on orbit, I could do it on the ground, and I was able to get it into my dissertation.
Fantastic. Wow. Serendipitous moment. Love that. Yeah. Garrett, you must have a bunch you could talk about.
Well, yeah, at the top of the list would have to be the 3 spacewalks I did, because those were the most challenging and the most consequential moments of my space flights that I was responsible for. So you train for years to get ready for this, and you have 7.5 hours to get it right, and only this one chance. It's quite a lot of pressure. As you're about to get into the airlock, it's a similar thing. I've never played professional athletics, but I've talked to people who had. And it's kind of like when you have that one chance at a championship, whether that be a World Series or a World Cup or whatever that championship might be. As you take the field, you know that whatever transpires in the next few hours is going to identify you, or is going to define you, maybe for the rest of your life. And when you're old and sitting in your rocking chair, you're going to reflect back to that moment with either a great sense of satisfaction or a tremendous sense of regret. And that's a lot of pressure, actually. But when you come back and it worked, and you accomplished all your objectives and you're back inside safely, that's an incredible feeling. But I'll also say that a close second was being part of a team that did something amazing, even though I had no direct contribution necessarily. So when I was at SpaceX and we got the first cargo Dragon up to the space station, and then later, when we had a successful first launch of the Falcon Heavy rocket, I had no direct involvement with either one of those 2 projects. I was working on the crew vehicle at SpaceX. But standing there with the entire team, cheering, watching it happen live on the video as we saw those 2 things transpire, was so gratifying. Just to be part of a group that could do something that amazing. That's why this industry, this business that we're all in of space exploration is so powerful, and it is such a great thing to do for your career, because you can have moments like that where you are part of something great, even if you're not at the tip of the spear.
Yeah. Now I'm going to throw the ball to your court, Jim. I'll give you a chance to say a shout out to a dear friend and colleague that you studied with, who happens to be on the International Space Station now, has that SpaceX affiliation. He trained at Caltech along with you. So if you want to give your buddy a shout out for his 50th birthday, why don't you do so?
Yeah, it's tomorrow, right? So apparently tomorrow is Bob Behnken's 50th birthday. So Bob, if you're watching Facebook Live on the space station, which is actually possible, happy birthday. and looking forward to what a great week in space, by the way. We got the launch of this incredible mission. And then if all goes well and the weather cooperates, later on in the same week, we'll have the return of the first Crew Dragon with Bob Behnken and Doug Hurley, 2 NASA astronauts on board. So if you're a space geek like I am, and I think the rest of us on this panel are, you can't ask for a much better week.
Thank you, Garrett. Okay, one last question, and we'll open up for questions from our audience, and it has to do with the future. So we've gone back and forth in this country between should we go to the moon, should we go to Mars, should we go to the moon, and that policy has shifted almost with every congressional election. Not quite, that was kind of a joke, but nonetheless, are we on the right track now as a country? We're going back to the moon. There's a lot of the Artemis project and other projects that NASA has publicly announced as part of their plan. We're going to set up a lunar base, and we're going to use the lunar surface as a base of operations and a place to practice. Does that make sense? Is it consistent with the mission that we've been talking about today? And is it consistent with the long-term goal of putting boots on the ground on Mars? What do you think? Are we headed in the right direction, or would you revise our policy perspective on that?
I'll take the first one on that. So I think all investments in human spaceflight are the right thing to do. I mean, I'm a fan of going to Mars. I want us to do both. I want us to go to the moon and set up a colony there and research base there, as well as go to Mars. But ultimately, I think what I see as amazing is the investment in the commercialization of space, which ends up enhancing competition, ends up enhancing collaboration, which ultimately will reduce the cost of sending people to space, which facilitates more exploration, which means you could do both the moon and Mars. So I think we are on the right path.
Great. What about you, Garrett? How fast could we actually get a crew on Mars?
Well, first of all, let me say that, it really depends on what the objective is as far as, which destination you pick to go to first. If your objective is, particular scientific investigation about the geology of the moon, then obviously you want to go to the moon. But if the objective is a long-term human presence somewhere else in our solar system, then Mars is the place to go. And Mars, for all the reasons we've talked about already, is, I think, a much more attractive destination as far as what we can learn scientifically about the possible presence of life. And as far as the potential to have a permanent, sustainable human presence on another place in our solar system, the moon is not going to cut it. There just aren't the in situ resources that you need to sustain that. So if the objective is survival of the species, if you take the very big picture view, then you really need to go to Mars. So the question then boils down to, well, what can you learn on the moon that would help you get to Mars either safer or more rapidly? And I think the biggest thing that the moon can help us with is helping to understand the effect of the radiation in the space environment on human beings. We know very well what radiation is out there, but we have still a lot that we don't understand about what that radiation does to human tissue. And until we actually start sending people and living for extended periods of time in these environments and try different types of engineering solutions, we really won't know how dangerous it is to send humans to Mars. And so that's something that I think we can learn on the moon that would be potentially very valuable.
It's true. Yeah, I guess that's true. Yeah. There's no air on either place, essentially none on Mars. Can you do farms on Mars? According to The Martian, you can. And what's the weather like there? I mean, those are the things that I guess the robotic probes that we're sending forth will sort of, it will inform those kinds of things that we as humans will have to go back and do. Professor Nielsen, before we turn to questions for the for the audience, and I don't see any here, maybe I'm not looking at the right place in my panel, but I wondered if you had anything to say about that last question.
Well, I would agree with both of my colleagues here, but mostly I look at it from the life situation. There are things we just don't understand yet. One is the long-term effect of microgravity. The other is living without a magnetic field, which means that you'll be exposed to tremendous amounts of radiation. It was my hope that we would get some insights into that through the space station, but it hasn't really happened. We don't, and I think the moon really is a great place to test some of these things out. This old war that I see between manned missions and robotic missions is just silly. I think we need them both. You certainly are not going to send manned missions for the foreseeable future to Saturn and Jupiter and the moons that we want desperately to discover there. And maybe if we would get our act together and make this an international project instead of a battle between countries, it wouldn't seem nearly so expensive. And that would be my hope for the future, that we could all agree. And Anita said it before, but if we discover life someplace, that could very easily happen. I think that it would be a uniting kind of thing. Yes. That would be tremendous for the entire planet, our species. So.
Thank you. So we do have a couple of questions coming in. One is, what do sci-fi movies get right or wrong about Mars?
I would say it depends upon the movie. So The Martian, I think, did a lot on getting it right from a technology perspective. My only nits with The Martian were the premise of the movie that they lost communication. I feel as though they would have had more than one antenna and they would have been able to see from orbit that things are okay. And also, I think the dynamic pressure of the loads that were on the Mars Ascent vehicle that pushed it over. But other than that, I would say that movie got it right. The other ones, not so much, like Mission to Mars, and those were a little bit more fantasy, I think. That's just my opinion.
I love that a lot.
It's funny. I met Andy Weir once, the author of The Martian, and he asked me how I liked the book, and I said I didn't like it, and he said, oh, and he jumped right to what Professor Sengupta said there. He said, he jumped right to like, oh, was it because we didn't have redundancy in the comm system? And I said, no, I was okay with that. And he said, was it because the dynamic pressure on Mars really wouldn't be sufficient to knock a structure off the roof of a habitat? And I was like, nah, I was okay with that. And he asked, well, why didn't you like it? And I said, listen, I work all day at SpaceX on space operations, okay? I come home and at night, I'm exhausted, but I'm reading your book. And it's like, I have 84 souls to travel 6,000 kilometers, and I have 72 moles of hydrazine, and I got, and I'm reading all this, and I'm like, it's like I'm still at work. Okay?
Yeah,
I don't want that. So, but actually, that movie really did get it right, and that book really got almost everything right. Yes.
So, a question again, specifically to Mars: what is the air like on Mars? Is there air, and can you do farms on Mars? That was a question that actually came from one of our guests. And what's the weather like? Anybody? What's the weather like on Mars?
Just I can take that one from at least an engineering requirements perspective. So the wind velocities are actually quite high. I think it can get up to like 50 meters per second. It depends upon what altitude you're at, but because the density is really low, it ends up not being that much of a force. In terms of a temperature variation, in the equatorial region in the middle of the summertime, it actually can be like a wintertime day from a temperature perspective that you see in California, like 40 degrees Fahrenheit on the high side, but on the low side, it's well into the I think probably like minus 180 degrees at nighttime. So you have a huge temperature variation, which makes it very difficult to design a vehicle because it has to keep itself warm at night and has to prevent itself from overheating during the day if it has a RTG on its back, for example. But the atmospheric composition is primarily carbon dioxide. It does have other constituents in there, which means you could extract things, or you can split up the carbon dioxide to get oxygen, like MOXIE is going to do.
Mm-hmm. Do other worlds hold an appeal at this time because Earth has such major problems like the pandemic? Are we looking seriously at other places for reestablishing our human existence?
Well, I think all of us are big advocates for exploring Mars and potentially one day settling humans there. But I think one thing to keep in mind is, as attractive as that might be, and I would love to see Olympus Mons, to see, a mountain that makes Mount Everest look like a molehill, and canyons that are the size of the United States. I would love to see those things. But keep in mind that living there is not going to be easy. I mean, it's more forgiving in a lot of ways and a lot easier to live in Antarctica. And we don't have like housing developments in Antarctica right now.
That's true.
So I think one of the things that working in this field makes you understand is, and especially for those of us who have been fortunate enough to leave Earth temporarily, it makes you appreciate just how special this place is. And I think the most important lesson we could take away from that is not, hey, let's come up with plan B or planet B and let's all pack up and move to Mars. It's, hey, let's take care of this thing that we have, which is where human life evolved. We are ideally suited for this planet as far as what we drink, what we eat, what we breathe. This is where we grew up, and there's no place better than this, and we should take care of this one.
I think that's a nice final answer. I've just been given the signal it's time to leave. This hour has gone by incredibly quickly. I'm so sorry we don't have more time to chat. I'd like to thank our panelists again, Professor Ken Nielsen, Professor Anita Sengupta, and of course, Dr. Garrett Reisman, my colleagues from USC. This has been a wonderful, wonderful chat. I hope we'll continue it again some other time. I'd like to ask our audience to please remember to like and share this video. This has been an absolute delight. And let me wish everyone the very best going forward. All success in your missions. Bob Behnken, Godspeed on that International Space Station. Happy birthday again. And everybody be well and stay well. We're all in this together.
Thanks for listening. Be sure to subscribe to our podcast and visit us at podcast.usc.edu.